Welcome to the deep dive. We often talk about looking out at the universe, but actually seeing it, especially the really distant, powerful stuff, that's a huge challenge. Think back to the mid-20th century. Scientists were seeing these incredibly powerful cosmic giants way out there, and they were asking, profound questions like, what on earth is powering these things? Answering that depended entirely on getting a clearer view across just unimaginable distances.
Exactly. And that challenge, that need for a clearer view, leads us straight into today's topic, radio telescopes. Specifically, we're diving into this really revolutionary technique called aperture synthesis. Our guide here is Martin Ryle's amazing 1974 Nobel lecture. It really lays out how they overcame these, well, seemingly impossible obstacles to build instruments far more powerful than anything before.
Right. So that's our mission for this deep dive. We're going to unpack that whole journey from, pretty basic fuzzy observations to these incredibly detailed cosmic maps. We'll get into the ingenuity, some really surprising challenges they ran into, and of course, the huge discoveries that completely reshaped how we understand the universe.
Okay, let's set the scene. It's 1952. Scientists make this startling discovery about Cygnus A. It's a galaxy, incredibly distant, 1,000 million light years away. And it's not just emitting radio waves, it's like screaming them. 1,000,000 times more intense than our own Milky Way, or even Andromeda.
1,000,000 times. It was just off the charts, and nobody had a clue what mechanism could produce that kind of energy. It was a total mystery.
Wow.
And this wasn't just some, weird cosmic object. It had huge implications. It suggested really strongly that if we could just build better radio telescopes, more powerful ones, we might finally be able to test different cosmological models, figure out how the universe actually works on the grandest scale.
But the telescopes back then were...
Pretty limited, right?
Oh, absolutely. The biggest problems were angular resolution, basically. How sharp the image was, it was poor, everything looked fuzzy, sneered out. You couldn't easily tell two nearby sources apart, couldn't map any detail within a source.
Just blobs.
Pretty much. Yeah. And positional accuracy wasn't great either. They found lots of sources, but many just looked like points, maybe 2 or 3 arc minutes across at most. No real structure visible.
Okay, let's unpack this core engineering problem then, because it sounds fundamentally difficult.
It was. The issue is the wavelength. Radio waves are long. Compared to optical light, their wavelengths are about 1,000,000 times greater.
1,000,000 times, okay.
So think about the resolution of your own eye. It's about 1 minute of arc, right? To get that same sharpness with radio waves, say at a 50-centimeter wavelength, you need a telescope dish that was 1 kilometer in diameter.
Kilometer? That's enormous. How would you even build that?
Exactly. And it's not just the size. The precision needed is staggering. The surface of that kilometer-wide dish would need to be accurate to, well, the term is lambda over 20, lambda being the wavelength. So for a 50-centimeter wave, that's an accuracy of just a few centimeters across the entire kilometer structure.
Wow, just a tiny bump over that massive area would ruin the image. The engineering challenge seems almost insurmountable.
It really was monumental.
Yeah.
Now, things did get a bit better around 1960. Masers and parametric amplifiers came along.
Okay, what did they do?
They basically acted like super-sensitive receivers, especially at centimeter wavelengths. This meant you could build, reasonably sized dishes, maybe 10 to 100 meters across, and these could achieve roughly that 1 arc-minute resolution we talked about.
Ah, okay, so some progress.
Some progress, yes. But to get better than 1 arc-minute with a traditional rigid dish, the engineering problems, the sheer stiffness required, it was still incredibly difficult and expensive. They were hitting a wall.
So the conventional approach wasn't cutting it for pushing the boundaries. They needed something new.
Precisely. They needed an entirely different approach. And that's where Martin Ryle and his team at Cambridge came in. They spent 20 years developing this idea. Aperture synthesis.
Aperture synthesis.
Yeah.
Okay, break that down. How does it work?
Well, instead of trying to build one single, impossibly huge dish to collect the radio waves, the idea is to measure the wave field over a large area, but do it piece by piece, and then combine those measurements mathematically.
Piece by piece. Like?
Think about how a normal telescope dish, a paraboloid, focuses light. Or maybe an array of simple dipole antennas all wired together. They both combine signals arriving across an area. Aperture synthesis takes that idea, but flips it.
Okay.
Here's where it gets really clever. You only actually sample a small part of the incoming wavefront at any one time, using small antennas or elements. But then you move these small elements around to different positions, effectively occupying all the spots where parts of your imaginary giant dish would have been.
Ah, so you're building up the aperture, the collecting area, over time by moving smaller pieces.
Exactly. And the key, the absolute linchpin, is using one element as a phase reference. This lets you precisely track the phase relationship between the signals received at different times and different positions.
Phase reference. Okay, so that keeps track of how the waves line up.
Precisely. Without that, combining signals from different times wouldn't work. With it, you can take all those measurements from different spots and different times and feed them into a computer. And the computer synthesizes, or creates, the image that the giant full dish would have produced.
Okay, that sounds incredibly smart. But my first thought is, wouldn't that take forever? Moving antennas around, observing piece by piece.
That's the intuitive thought, right? And yes, you do need to make observations with many different relative positions of the elements. The number scales roughly as the big dimension squared divided by the small element dimension squared. But here's the kicker. The way the data is combined in the computer allows you to map a large area of the sky simultaneously.
Ah, okay, so you're not just mapping one tiny spot with each measurement?
Exactly.
Hmm.
So the total observing time ends up being pretty much the same as if you could have built that single giant instrument. The bottleneck wasn't observing time. It was computing power, as we'll see.
And what about the quality, the sensitivity? Is it as good?
Well, the sensitivity is much better than just using the small elements alone, obviously. The final signal-to-noise ratio you get is roughly equivalent to an instrument with a collecting area about 3 times the overall diameter times the size of one small element.
3DD.
Oh.
Okay, so maybe not quite the full D squared of the hypothetical giant dish.
Not quite d squared, no. But here's the crucial part. It often exceeds the sensitivity of any instrument that could physically be built using conventional methods.
Wow. Okay, so it's a practical way to get performance that was otherwise impossible.
Yes, it avoids the huge structural problems and costs of massive dishes.
Yeah.
You get high resolving power and a large effective collecting area for minimum cost.
But there's always a catch, right?
The catch is precision. Just like the surface of a conventional dish needs to be accurate, here, the relative positions of the small aerial elements and the electrical paths the signals take must be known and stable. And the accuracy needed is the same order better than lambda over 20. So you trade the challenge of building a giant precise surface for the challenge of precisely positioning smaller elements and managing signal paths.
Interesting trade-off. Did this idea come out of nowhere, or were there earlier steps?
There were precursors. People in Australia and England had done early work mapping the sun using spaced antennas, but they assumed the sun was symmetrical, so they didn't need the crucial phase information. They also did some early mapping of our own galaxy's plane.
But the first real synthesis instrument capable of mapping anything complex.
That was built in Cambridge in 1954 by John Blythe. It's quite ingenious for the time. It used a long, fixed, trough-like antenna and a smaller movable one. The movable one was placed at 38 different positions along a line perpendicular to the long one. This setup effectively synthesized a square aperture, giving them a resolution of 2.2 arc minutes at a wavelength of 7.9 meters. And with it, they produced the first truly detailed maps of the galaxy's radio mission at that long wavelength. It proved the concept worked.
And Cambridge kept building bigger and better ones after that, right?
They did. They built another one at 7.9 meters with 45 arc minute resolution, and then one at 1.7 meters wavelength that achieved 25 arc minutes resolution. That 1.7 meter one was incredibly productive. It was used to map the northern sky and located nearly 5,000 radio sources.
5,000. That's amazing. You mentioned cost effectiveness earlier. How did they manage to build these relatively large instruments?
It was pretty clever, especially for the longer wavelengths, like over a meter. They didn't use solid dishes. They used thin wires, like 1 millimeter thick, just stretched across simple wood or parabolic frames.
Thin wires, like a wire mesh.
Essentially, yes. Very cheap to build. Ryle mentions it cost about £2 per square meter back then. Really allowed them to get large collecting areas without breaking the bank.
But that approach must have had its limits, too.
It did. 2 main problems emerged as they pushed further. At these long meter wavelengths, the Earth's ionosphere, the upper atmosphere, causes irregularities that distort the incoming radio waves. That messed up the phase measurements.
Ah, the atmosphere getting in the way.
Always. And at shorter wavelengths, say below 50 centimeters, where you want to go for better resolution, those simple wider structures just weren't practical. They'd get blown around by the wind, twist. You lose the precision.
Right, you need something more rigid.
Exactly. Which meant more solid and therefore much more expensive structures. So this kind of pushed them back towards the original concept, the one Ryle had thought about earlier,
Yeah.
using just 2 small but precisely positionable elements.
Okay, so they're back to needing to move these smaller elements precisely over large distances, which is the core challenge. How do they finally crack that?
This leads to arguably the most brilliant insight in the whole story, using the Earth itself.
The Earth. How?
They realize that the Earth's rotation naturally provides the relative motion between the antennas, as seen from a distant cosmic source. You don't necessarily have to physically move the antennas along rails all the time.
Wait, so the Earth turning does the work for you?
Precisely. Think
Yeah.
about it. If you have two antennas, say, near the North Pole, and you point them at the celestial pole, the point the sky appears to rotate around then over 24 hours as the Earth spins. The baseline connecting those two antennas effectively sweeps out a circle relative to the source. You get all the different orientations and spacings needed to synthesize a circular aperture just by letting the Earth turn.
That is incredibly clever, just using our planet's own movement. Did they test this Earth rotation synthesis idea?
They did. Ryle and Ann Neville set up an experiment in 1960-61. They couldn't afford two separate steerable dishes yet, so they cleverly used parts of a large existing cylindrical antenna to simulate two 14-meter dishes. By tracking a source for 12 hours, you only need half rotation. Due to symmetry, they synthesized an effective aperture of 1 kilometer.
Wow. And did it work?
Fantastically well. They achieved a resolution of 4.5 arc minutes at 1.7 meters wavelength. But more importantly, the sensitivity was amazing. They detected sources 8 times fainter than any previous surveys.
8 times fainter. That's huge for cosmology, for seeing deeper into the universe.
Absolutely crucial. It proved Earth rotation synthesis wasn't just clever, it was incredibly powerful.
And it works anywhere, not just the North Pole.
Yes, as long as your antennas are placed along an east-west line and they can track the chosen spot in the sky as the Earth rotates, you trace out elliptical paths in the aperture plane instead of circles, but it works just the same.
And the advantages must have been huge. Less physical moving of heavy gear, less land needed.
Exactly. That engineering simplicity and cost saving led directly to the next generation of major instruments built at Cambridge, the half-mile, the 1-mile, and ultimately the 5-kilometer telescopes.
But there was another piece of the puzzle, wasn't there? Something about computers.
Ah, yes, the unsung hero. You absolutely cannot talk about aperture synthesis without talking about computing power. It's fascinating, actually. Ryle mentions in his Nobel lecture that he'd actually worked out the principles for Earth rotation synthesis way back in 1954 in a notebook.
1954? That's years before they built the test instrument. Why didn't they build it then?
Simple. Computers weren't powerful enough. His note literally says they didn't build it because there were no computers with sufficient speed and storage capacity to do the Fourier inversion of the data.
Wow. So the idea was there, but the tech to actually process the data just didn't exist yet. What was the scale of the problem?
It was immense.
Yeah.
He gives an example. EDA-SAXII, a pioneering computer from 1949, to process just 4 minutes of data from a 24-hour scan using a relatively simple 38-point transform, took EDA-SAXII 15 hours.
15 hours for 4 minutes of data.
Right. So doing the full two-dimensional Fourier transform needed for Earth rotation synthesis for a whole 12 or 24-hour observation, he just writes it was not practicable, impossible with the tools they had.
So what changed? When did the computers catch up?
The first big step was EDA-SIXIC, which came online in 1958. And critically, David Wheeler at Cambridge developed an early version of the fast Fourier transform algorithm.
The FFT, that's famous now.
Indeed. But Wheeler developed it about 6 years before it became widely known and used elsewhere. This algorithm was a game changer for efficiently processing the synthesis data. Even with EDS-SEX and the FFT, reducing the data from that first 1.7-meter Earth rotation experiment still took the whole night of computer time.
The whole night, just to process one observation.
Yep. The real leap came with a Titan computer in 1963. That finally provided the necessary power to handle the data volumes from the upcoming 1-mile telescope. It really shows how aperture synthesis and the development of computing were completely intertwined. One couldn't advance without the other.
Okay, so armed with Earth rotation synthesis and growing computer power, let's talk about those big Cambridge instruments. The 1-mile telescope came first, in '64.
That's right. It used 3 18-meter dishes. 2 were fixed, and 1 could be moved along a half-mile, 0.8-kilometer railway track.
Why 3?
Very clever design.
Mm-hmm.
Having 2 fixed dishes and 1 moving one meant that for every position of the movable dish, you actually got 2 different baseline lengths. Simultaneously, the distance from the mover to each of the fixed dishes doubled the data rate, essentially. Very cost-effective.
Smart. And what was its main goal?
2 main things. First, push cosmology by detecting much fainter, more distant radio sources. Ryle shows maps going 100 times fainter than previous ones to really probe the early universe. Second, start mapping the structure of individual sources in detail to figure out the physics, what makes them tick.
Then came the half-mile telescope. Sounds like a smaller
It
version.
was actually built using the same rail track as the 1 mile, very cheaply. They got 4 smaller, 9-meter dishes, basically, for scrap metal prices.
Resourceful.
Very. And its niche was different. It was mainly used for mapping neutral hydrogen gas in nearby galaxies, studying how galaxies form and evolve.
And the biggest one, the 5-kilometer telescope in 1971.
Yes, the 5-kilometer. This one was purpose-built for high-resolution mapping of individual sources. Its goal was incredible detail.
And the resolution was?
Phenomenal for the time. Down to about 2 arc-seconds at 6-centimeter wavelength routinely, and even 1 arc-second under good conditions. That's comparable to large optical telescopes on good mountain sites, finally seeing radio sources with optical sharpness.
How did the 5-kilometer achieve that? More dishes.
Yes, and a more complex setup. It used 4 fixed dishes and 4 movable ones, all 13 meters in diameter, spread over 5 kilometers. Having 8 dishes meant you got 16 different baseline spacings simultaneously with each observation.
16 at once, so you could fill in that aperture plane much faster.
Exactly. A full, high-quality 2-arc-second map could be made from a single 12-hour observation run.
But the precision needed must have been even more extreme over 5 kilometers.
Absolutely mind-boggling. The relative positions of the antennas and the lengths of the cables carrying the signals had to be known and kept stable to better than 1 millimeter. Ryle quotes the measured distance between the outer fixed dishes over 3.4 kilometers, determined to an accuracy of plus or minus 0.25 millimeters. And it stayed stable for years.
That's just hard to fathom, controlling things that precisely over kilometers.
And it needed an online computer, controlling the telescope pointing, tracking, applying corrections in real time, and generating the map pretty much as the observation happened. The peak of synthesis tech at the time.
So with these amazing instruments, what kind of discoveries poured out? You mentioned starbirth.
Right, this was huge. Radio waves can see through the dense dust clouds where stars are born, clouds that are totally opaque to optical telescopes.
So you can see inside the stellar nurseries?
Precisely. Ryle gives a great example.
Yeah.
NGC 7538. The 1 mile telescope mapped it first, saw a diffuse cloud of older stars, but also this compact blob to the south. Looked interesting.
Hinting at something younger.
Maybe. Then they pointed the 5-kilometer telescope at that compact blob, higher resolution. And bam, inside it, they resolved 2 distinct, incredibly young stars. One was a hot, massive O-type star, the other maybe only a few thousand years old. Both were also detectable by their heat, their infrared emission. They were directly imaging brand new stars still wrapped in their dusty cocoons.
Incredible, seeing stars being born. What about those powerful extragalactic sources, like Cygnus A?
Ah, yes, the radio galaxies and quasars. These things are monsters.
Hmm.
In relatively short phases, cosmically speaking, they pump out maybe 1060 ergs of energy, equivalent to converting the entire mass of a million suns completely into energy via EMC2.
Just staggering amounts of power.
And the maps revealed where it came from. Yes, and it was surprising. The maps, like the famous one of Cygnus A, made with the 5 kilometers, showed the energy wasn't coming from the central galaxy itself, mostly. It was coming from 2 enormous lobes, huge regions filled with energetic particles and magnetic fields, located far outside the visible galaxy, often symmetrically placed on either side. There's usually just a weak radio source in the galaxy's core.
So the energy is generated in the middle, but dumped way out there.
That's the conclusion. It implies energy isn't produced in one giant explosion like a supernova on steroids. Instead, it seems the central nucleus of the galaxy produces energy, perhaps in the form of jets or beams, continuously, or at least over a very long period, maybe 10 to 100 million years. And these beams inflate these giant radio lobes way out in intergalactic space.
Do we understand how those beams work?
Still a huge area of research. The exact mechanism transporting that energy over hundreds of thousands of light years is still debated. But the detailed maps from aperture synthesis were absolutely crucial for revealing this structure and framing the questions.
And you mentioned the 5 kilometers had some unexpected uses too. Astrometry. Timekeeping.
Yes, that was a bonus. Because the positions of the antennas were known so precisely, they could measure the positions of compact radio sources on the sky extremely accurately. Good enough to contribute to defining the fundamental coordinate system of the sky, competitive with the best optical methods. And by timing the arrival of signals, they could measure astronomical time variations very precisely, down to milliseconds. A very versatile machine.
So looking ahead from 74, What was seen as the next big hurdle?
The same old enemy, the Earth's atmosphere. It's the ultimate limit for both optical and radio.
But it affects them differently, right?
Right. Optical astronomers worry about small-scale turbulence, maybe 10-centimeter pockets of air that make stars twinkle and limit resolution to about an arc-second typically. For radio waves, those small scales don't matter as much because the wavelengths are longer. But larger-scale variations in the atmosphere's refractive index, especially due to water vapor in the troposphere, become the main problem.
Water vapor. So humidity.
Basically, yes. Variations in water vapor content over kilometer scales distort the incoming radio wavefronts, messing up the crucial phase measurements needed for synthesis.
What kind of distortions did they actually observe with the big Cambridge telescopes?
They saw two main types. One was on a scale of about 0.7 kilometers, seemed linked to daytime heating, turbulence, often even in clear air, worse in summer. The other was much larger, 10 to 20 kilometer scale variations. The cause wasn't clear, maybe weather patterns, and it didn't change as much between day and night or season to season. But it was always there, blurring the potential sharpness.
Still, you said there was potential for even better resolution.
Oh, yes. Under really good atmospheric conditions, which Ryle estimated happened maybe only 1% of the time, the distortions could be incredibly small.
And when would that be?
Interestingly, often during widespread winter fog, when the air is very stable, saturated, the variations smooth out.
Fog. So bad weather for optical is good for radio.
Sometimes. In those rare, foggy, stable conditions, the distortions over 5 kilometers could be less than 0.2 millimeters. That meant potentially you could push to wavelengths as short as 4 millimeters and achieve resolution better than 0.2 arc seconds.
Wow, significantly better than even the 5 kilometers usual best.
Exactly. It really highlights how different the ideal site requirements can be for optical versus radio astronomy.
So for the other 99% of the time, the future lay in finding ways to correct for the atmosphere.
Yes. New techniques were needed.
Yeah.
One idea mentioned was building a second, smaller antenna right next to each main antenna in the array.
Why two?
The second antenna would constantly observe a nearby, bright, known point source, a calibrator, by seeing how the atmosphere affects the signal from the calibrator, whose true signal you know. You can figure out the atmospheric distortion second by second and apply a correction to the signal coming from your actual science target. Continuous phase correction.
Clever. And that leads towards techniques like VLBI, right? Very long baseline interferometry.
Exactly. VLBI takes synthesis to the extreme, using antennas thousands of kilometers apart, basically creating a telescope the size of the Earth.
Giving incredible resolution.
Resolution down to milliarc seconds, even microarc today. Truly phenomenal zoom. But VLBI has its own challenge related to aperture synthesis.
Which is?
Even with antennas spread across the globe, you still only have a handful of them, maybe 5, 6, 10 stations back then, a few dozen now. Compared to the size of the Earth-sized dish you're synthesizing, that's incredibly sparse sampling.
Very poor aperture filling, as you called it earlier.
Extremely poor.
Yeah.
So while you get amazing resolution on very tiny details, the field of view over which you can make an unambiguous map is very small, maybe only 0.02 arc seconds wide back then. You can't easily make detailed maps of larger structures.
So VLBI is great for zooming in on tiny cores, but not for the bigger picture.
Right. It's vital for understanding the absolute central engines of things like quasars.
Yeah.
But for mapping the larger structures, the jets, the lobes, you still need techniques like those used by the Cambridge telescopes, maybe extended, that provide better aperture filling at intermediate resolutions.
It's really been an incredible journey, hasn't it? The 25 years leading up to Ryle's lecture saw such a dramatic leap in what radio telescopes could do. And like you said, that directly led to understanding so much more about these really energetic, frankly weird objects in the universe and about the cosmos as a whole.
It truly transformed the field. It opened a completely new window, revealing processes hidden from optical view. Which brings us to a final thought for you, our listener, to maybe ponder. We've heard how aperture synthesis let us peer through dust to see stars being born and map these giant invisible structures around galaxies. Imagine, just for a moment, if we could overcome those atmospheric limitations completely. Not just for that rare 1% of foggy winter nights, but all the time, for all radio observations. What further secrets, what deeper understanding of how stars form, how galaxies evolve, maybe even the very earliest moments of the universe could we unlock then? What would those perfectly clear, deep radio maps of the cosmos truly show us?